Today, we capture black holes using planet-sized telescope arrays. But the mathematics that proved they exist started in the freezing mud of the Eastern Front in 1915. A German astronomer named Karl Schwarzschild was calculating artillery trajectories while suffering from a fatal autoimmune disease. Between bombardments, he read Albert Einstein's newly published equations of general relativity, the theory describing how mass curves space and time. Schwarzschild solved Einstein's equations exactly, but in doing so, he found a severe mathematical glitch. This is a diagram showing the fabric of space-time reacting to mass. Schwarzschild calculated that if you compress enough mass into a small enough volume, the curvature of space-time effectively snaps. It creates a boundary where the required escape velocity exceeds the speed of light. Cross this boundary, known as the event horizon, and no path points back out. Schwarzschild mailed his solution to Berlin shortly before he died. The mathematics were flawless, but the physics community refused to accept the physical result. They assumed nature would somehow step in and prevent matter from ever compressing that far. That skepticism was championed by titans of astronomy like Arthur Eddington. In 1919, Eddington observed a solar eclipse, proving Einstein's broader theory by showing that the sun's mass actually bends starlight. Yet Eddington publicly ridiculed the idea of a star collapsing past the point of no return, dismissing it as a stellar absurdity. The math sat as an uncomfortable quirk until J. Robert Oppenheimer and Hartland Snyder looked at dying stars. In 1939, they proved that when a massive star exhausts its nuclear fuel, its internal outward pressure completely fails. Gravity takes over. Once that collapse begins, absolutely nothing in known physics can stop it. This created an immediate problem for astronomers. They now had a verified mechanism for creating these deep gravitational wells. But by their very definition, these objects trap all light. You cannot point a telescope at something that emits zero radiation. To prove these theoretical objects were actually out there, astronomers had to stop looking for the objects themselves. They had to learn how to track the dark mass by the destructive footprint it leaves on the space around it. Earth's atmosphere is opaque to X-rays, shielding the surface but blinding astronomers to the high-energy signatures of the deep sky. Detection only began when sounding rockets and satellites rose above the air to record radiation from gas being shredded by unseen mass. This animation shows an accretion disk, a swirling vortex of gas. It spirals and collides at immense speeds, superheating the matter. This converts mass to energy, dwarfing nuclear fusion. Scaled up into a quasar, a single solar system-sized engine outshines its entire host galaxy. But heat is only half the evidence. To truly weigh a dark mass, you have to watch things move around it. Astronomers used these massive infrared telescope arrays to pierce the thick dust at the center of our own Milky Way. They locked onto a star named S2 and tracked it for decades. S2 flies in a tight, violent elliptical orbit, reaching blistering speeds as it whips around a completely dark point in space. To force a star to move that fast on that trajectory, the dark point, known as Sagittarius A star, must contain 4 million times the mass of our Sun, packed into a microscopic volume. Orbital mechanics and X-ray heat converged to place a massive, dark engine exactly where the equations predicted. Still, everything observed up to this point relied on the glowing matter caught outside the horizon. To capture the object itself, physicists had to abandon light entirely and build machines capable of feeling the literal distortion of spacetime. In 2015, the LIGO Observatory, using 4 kilometers of steel, vacuum, and laser light, registered a fluctuation smaller than an atomic nucleus. It was a sub-second chirp. That acoustic signal matched the exact spatial ripple predicted by relativity for 2 stellar mass black holes colliding in deep space. With the sound of a collision recorded, the final prize was a picture. The Event Horizon Telescope collaboration linked radio observatories across the planet to create a synthetic, Earth-sized lens. Their target was the supermassive black hole at the center of the giant elliptical galaxy, Messier 87. In 2019, they resolved this. The bright orange boundary is the photon ring, a halo of ultra-hot plasma orbiting outside the point of no return. The dark center is the shadow created by the event horizon itself, where gravity violently bends and permanently captures light. The diameter of that shadow perfectly matched the mass calculations predicted by Einstein's equations. A century after a dying soldier sketched it out in the mud, the extreme limit of general relativity had a physical, visual form. Proving that black holes exist did not finish the physics. It created an unsolvable contradiction. They perfectly satisfy the rules of gravity, but they completely break the laws of quantum mechanics. In 1974, Stephen Hawking applied quantum field theory to the edge of the event horizon. He discovered that a black hole is not perfectly, permanently black. Over immense scales of cosmic time, it slowly leaks thermal energy. This diagram illustrates what we now call Hawking radiation. Empty space is constantly bubbling with pairs of entangled quantum particles. If a pair forms exactly on the boundary, one particle gets sucked in, while the other escapes as radiation. The escaping particle steals a tiny fraction of the black hole's mass. Because of this, the black hole slowly radiates away and will eventually evaporate completely into nothing. And that creates the information paradox. Quantum mechanics dictates that physical information, the precise structural blueprint of every atom, cannot be destroyed. But if a black hole crushes a star, holds it for billions of years, and then disappears into random thermal waves, the universe has permanently deleted that information. Physicists are left with a brutal choice. Either Einstein's description of a smooth, empty event horizon is wrong, or the absolute foundation of quantum mechanics is broken. They cannot both be true. This tension sparked the modern firewall debate. To save the rules of quantum information, some theorists argue that the horizon isn't an empty threshold at all, but a blazing wall of incinerating energy. Black holes are the ultimate cosmic stress test. They are the only places in the universe where the macrophysics of heavy gravity and the microphysics of quantum mechanics are violently forced into the same room. It has been a 100-year journey. What started as an unwanted calculation in a freezing trench has become the central battleground for a unified theory of everything. Every other object in the universe is defined by the matter it contains. A black hole is defined only by its silence. To explore this absolute limit of human knowledge, read Black Holes: The Edge of Reality.